Hello everyone, I am Serkan Güldal from Adıyaman University. Today I will be presenting on physically realistic synthetic data generation for crystal structure using the Metropolis algorithm. This technique is important for generating realistic simulated data, especially when experimental data is limited or costly. We will be using Metropolis algorithm, a powerful statistical method, to create these synthetic crystal structures that closely resemble real-world materials. These datasets are valuable for testing, validation, and advancing our understanding of crystal behavior, particularly in machine learning applications. Let's begin. In material science, one of the major challenges is data scarcity. Experimental datasets are often expensive, time-consuming to produce, and limited in scale. Similarly, quantum models are computationally expensive. Yet, machine learning models require large volumes of high-quality data to accurately predict material properties. To address this, synthetic data generation offers a scalable and cost-effective solutions. By using simulation-based approaches, we can produce physically meaningful datasets that mimic real-world behavior. Our proposed solution leveraging synthetic data to accelerate the materials discovery and support machine learning applications. Initial crystal structures such as face-centered cubic, body-centered cubic, and hexagonal closed pack are commonly used to represent the atomic arrangement in solid materials. A 3 by 3 by 3 unit cell configuration is selected to create a supercell large enough to capture local structural variations while remaining computationally efficient. Atomic positions are randomly perturbed with a narrow range of plus minus 0.02 units. These small perturbations simulate thermal motion and introduce configurational diversity, allowing the system to explore nearby states in the potential energy landscape. The energy of each perturbed configuration is evaluated using interatomic potentials. Lennard-Jones potentials captures van der Waals interactions. Coulomb potentials accounts for electrostatic forces, and Morse potential models bonding interactions. These models provide a physically meaningful basis for estimating the stability of atomic arrangements. The Metropolis acceptance criterion is applied using the probability expression, where delta E is the energy difference between the current and proposed configuration, K is the Boltzmann constant, and T is the system temperature. This probabilistic rule favors energetically favorable configurations while still allowing occasional acceptance of higher energy states, ensuring realistic thermodynamic sampling. A temperature value of 5 is chosen to balance the exploration, the convergence, and it allows the system to escape the local energy minima while still favoring lower energy configurations, maintaining thermodynamic consistency throughout the simulation. We explore three fundamental physical potentials used to model the atomic interactions in crystal structures. First, the Lennard-Jones potential. This is widely used to simulate van der Waals forces between natural atoms. It features the steep repulsive term proportional to r to the minus 12, and attractive term is proportional to r to the minus 6. This balance makes it ideal for modeling noble gases and simple molecular systems. The equation shown captures this dual behavior. Next, the Coulomb potential, which describes the electrostatic interaction between charged particles. It is long-range and inversely proportional to the distance between charges. This potential is essential for simulating ionic crystals where charge-based interactions dominate. Finally, the Morse potential. This one is particularly useful for modeling covalent bonding and vibrational behavior in molecules. Unlike harmonic potentials, Morse allows us to realistically simulate bond stretching and dissociation, making it valuable for molecular dynamic studies. Each of these potentials contributes uniquely to the energy landscape of simulated crystal structures, and their selection depends on the type of the atomic interactions we aim to capture. Here is the step-by-step workflow we use to generate synthetic crystal structures using the Metropolis algorithm. We begin with the lattice selection, where we choose the type of the crystal lattice, FCC, BCC, HCP, and define the simulation parameters such as unit cell size and temperatures. Next, the atomic perturbation. Here we introduce a small random displacement to atomic positions This step adds configurational diversity, which is essential for exploring a wide range of structural possibilities. Then comes energy evaluation. We calculate the interaction energies of these perturbed structures using one of the three physical potentials, Lennard-Jones, Coulomb, or Morse. Each potential captures different types of atomic interactions. After that, we apply Metropolis filtering. This is a probabilistic step where configurations are accepted or rejected based on their energy change and the system temperature. It ensures thermodynamic consistency and filters out unrealistic structures. Finally, in the data export phase, we store the accepted configurations. These datasets are then ready for use in machine learning tests, such as energy prediction, phase classification, or structural optimization. This workflow ensures that synthetic data we generate is both physically meaningful and statistically diverse. The energy distribution results for three different physical potentials used in our simulations are presented here. Starting with the Lennard-Jones potential, we observe a narrow unimodal distribution centered around a negative energy value. This indicates that Metropolis algorithm has successfully filtered for stable configurations where attractive van der Waals forces dominate. The narrow spread also suggests low variability, meaning most accepted structures are energetically favorable. In contrast, the Coulomb potential shows a broader distribution with a positive mean energy. This reflects the nature of electrostatic interactions, especially in systems with like-charged particles. The wider spread implies greater variability in interaction strength, and the positive energy value suggests that many configurations are less stable under purely Coulombic forces. Finally, the Morse potential yields a Morse potential yields a symmetric and tightly clustered distribution at low energy. This pattern is characteristic of covalent bonding, where atoms tend to settle near equilibrium bond lengths. The clustering around the minimum energy value confirms that the algorithm favors physically realistic bonding behavior. Together, these distributions highlight how each potential influences the stability and realism of the synthetic crystal structures generated. The difference in energy distributions across the three potentials arises from the fundamental nature of the interactions they model. Lennard-Jones and Morse potentials both include attractive components that stabilize the atomic configurations, leading to negative mean energies and narrow distributions. These potentials favor configurations near equilibrium distances, where the system is energetically minimized, resulting in tightly clustered energy values. In contrast, the Coulomb potential models purely electrostatic interaction, which are often repulsive in systems with like-charged particles. This leads to higher positive mean energies and a broader distribution. As the system explores a wider range of less stable configurations, the absence of stabilizing attractive term in Coulomb model contributes to this variability. Overall, the shape and spread of each distribution reflect how each potential governs atomic interactions, whether by promoting stability through attraction or allowing greater fluctuation due to repulsion. When we summarize the key findings from our simulation study using the Metropolis algorithm, first, we achieved statistical diversity. The algorithm generated a wide range of atomic configurations with a varied energy landscapes, yet all remain physically plausible across the three potential models, Lennard-Jones, Coulomb, and Morse. Second, we ensured thermodynamic consistency by applying probabilistic filtering at fixed temperature by T equal 5. The accepted configurations follow Boltzmann statistics. This enhances the physical realism and quality of the datasets, which is crucial for machine learning applications. Third, we observed potential specific behavior. Each interaction model contributed distinct characteristics. Lennard-Jones favored equilibrium distance typical of the van der Waals forces. Coulomb captured long-range electrostatic effects, and Morse accurately modeled covalent bonding and vibrational dynamics. Finally, the result is a set of machine learning-ready dataset. These synthetic configurations are well suited for tasks like energy prediction, phase classification, and structural optimization, making them valuable asset in computational material science workflows. These findings demonstrate that simulation-driven synthetic data generation, when guided by physical principles, can produce high-quality datasets for advanced modeling and discovery. The practical applications and broader impacts of our synthetic data generation framework is important in many ways. Here is the three most impactful ones. First, in machine learning training. The synthetic data we produce help overcome data scarcity. These data sets are physically realistic and statistically diverse, which accelerates the development of predictive models, especially for tasks like energy estimation and phase classification. Second, the materials discovery, our simulation-driven approach, enables rapid screening of novel crystal structures. Instead of relying solely on experimental data, researchers can explore a wide range of configurations computationally, significantly speeding up the discovery process. Third, the structural optimization. The energy filtering configuration generated by Metropolis algorithm serve as excellent starting points. These structures are already thermodynamically plausible, which makes them ideal inputs for refinement algorithms used in computational material design. Overall, this framework bridges simulation and machine learning, offering a scalable and efficient pathways for advancing material science. Future directions. First, we plan to implement temperature-dependent simulations. By varying the temperature, we can explore phase transitions and thermal effects on crystal stability. This will allow us to simulate more realistic material behavior under different conditions. Second, we aim to incorporate hybrid potentials. This involves integrating many-body interactions model and machine learned potentials to improve the accuracy of the energy evaluations. These advanced models can capture complex atomic interactions that traditional pairwise potentials may miss. Third, we are exploring active learning strategies. By combining Metropolis sampling with adaptive feedback mechanism, we can iteratively refine the dataset's quality. This approach helps us to focus computational resources on the most informative configurations, improving both efficiency and relevance. Ultimately, this simulation-driven methodology contributes to accelerating materials discovery, offering a scalable and cost-effective alternative to experimental data collection. It supports the development of robust machine learning model and opens new avenues for predictive materials design. Thank you for your attention. I hope this presentation offered useful insights into simulation-driven data generation and its role in materials discovery. If you have any questions or want to discuss ideas, I will be happy to hear what you are about to say.